get going. So this is the last lecture for this semester for you, for C++. I wanted to cover a new topic, or at least expand on what I've done in the past on this. That's metaprogramming. Before I do that, quick check. You guys are in good shape with the homework that's due tonight? One head nodding. No? So how far along are you? Wow. Okay. So you're almost done. That's what I'm reading, I'm hearing. Come on, talk to me. Yeah.
We managed to get it going, but our statistics are messed up.
Your statistics are messed up. Okay. So you need debugging time. Another feedback? Who has it completely working? Okay, that's not very many. All right. So could you use some more time? Oh yeah, I see head nodding. Okay. You're shy. I don't know what happened. I know I've been away for a week, but I mean, things can have changed that dramatically in a week. Sure, I'll give you a little more time, right? What I care about is you getting this done, right? It's not so much the due date. So I'll give you another 2 days. I'll push back to Wednesday evening. So that should help you a little bit get it done, okay? Since also I was away, so you couldn't really come and ask me questions in my office, I'm back, so you can do that. Doesn't mean I won't go into hiding. You can try. All right, yeah, you had a question.
Oh, no. Nick, what's the threshold for how close the statistics should be to your
roughly? I mean, you can't get the exact same statistics as I do, right? The smallest changes in your implementation would bring you different statistics. What matters is that if my code reports on a certain system that yes, this queue is bounded and its length tend to be like 15, 16, I would expect yours to say, yeah, the queue is bounded, it's hovering around 15, 17, maybe. That's fine, right? As long as you're in the same order of magnitude. If all of a sudden, for a model, mine is saying, well, the queue is bounded or the wait time is on average 22.5 seconds, and you come back like, this isn't bounded, the wait time is about 2 billion years, there is a problem, right? So I want you to be roughly in the ballpark, but not necessarily spot on. I mean, it would be crazy for us. It's a simulation. We need to be reasonable. Okay? So 48 hours extra before you get the next homework, which is kind of neat. So you have a little extra time to get it done. Okay? Good. So back to the topic. So this is more like a traditional lecture, but feel free to stop me at any time, right? But I want to take you through this. So first, a refresher, right? Why are we doing metaprogramming, and what is the point in real life? Because the example we've seen so far with metaprogramming was quite minimalistic and maybe academic in a sense. We looked at how to do factorial. Geez, okay, that's great. It can be done, but why should I care? So I wanted to show you that you can do some things that are not as straightforward. So we'll go through that, and in particular, we'll see how you can actually do code generation, or at least something that's equivalent to code generation, but much better. We'll be using traits, const expression, and data structures for metaprogramming. So that should be kind of fun. The main idea for metaprogramming is to move tasks at compile time. Things that would happen at runtime, normally you do them at compile time. And it makes sense when these things do not depend that much on your data that you read at runtime, obviously. If it did, then it won't work. But the problem is that if you move certain tasks at compile time, you often have to use a different programming language. That's what's happening, for example, when you write a compiler. So how many people took compiler here? Get a sense? None. Okay, so that's not going to work too well. Who's used Yak? Bison? Flex? Oh, one person used flex. Okay, good. So these things, right? They're called compiler tool generator. That is, there are other languages you can write specification in, and they spit out C code or C++ code that you link with your executables in order to do a task. Which means that you're authoring part of your software in a different programming languages. And you have to kind of mix things. If you use SQL, that's kind of the same idea. You write SQL queries and you embed the SQL queries in your code, and you have your code being kind of a mix. And the interface between the two is not always straightforward. Okay? So the idea here is, okay, we want to have this kind of things where certain tasks are done at compile time, but I don't want to learn yet another completely different programming language. To do that, I want to do all the compile time stuff in my good old-fashioned C++. Right? No switch. We stay in the same language. So you'd like to reuse C++ as much as possible. It's just that the compiler will do certain things at compile time, more things than it used to, and that's going to generate something that you care about. Okay, so that's the main idea. So remember, the compiler does all the work. That's the main thing. In theory, you compile and you never run the program. The answer is the compiled code, right? That is, you can look at the compiled code, the answer is embedded in the compiled code. It's right there. Running it is just a way to maybe print out the answer that's embedded in the binary. But the answer is already in the binary. The compiler has done all the work, okay? And I make a point of doing that by showing you the machine code so that you get convinced that everything really did happen at compile time, okay? So that will be something kind of fun. So you already saw that. That's the factorial example. So if you recall, I turn around so that you can see this. That was factorial, and essentially this is my main program, not all that interesting. And I have two stanza here, and they're both defining structures. They're both structured. This one is struct fact with a template. This one is struct fact, and then there is a zero stuck behind. Okay? So there are two template definition of structures. Why? Because a structure is a type. When you are using metaprogramming, you are computing by generating lots and lots and lots of types. Why? Because the answers are embedded inside the type. You do everything by putting the result of your computation in types, which means any intermediate result is also embedded in a type. Everything ends up in a type. So it's not surprising that we have a struct. It's not because we have a struct in the traditional sense. That's because we want to embed the result of the computation in a type so that we can actually have the compiler do all the work. Now what you see, what you see here, is that the structure factorial is templated by an integer, which means actually I have a family of type. I will have factorial 10, factorial 9, factorial 8, factorial 5, 6, 7, 4, 3, 2. All of them will be there, right? This stanza can create a bunch of type for me. What each type contains is the same thing. It is a static constant integer. Each type inside of it has that thing. It's static and constant. Why? Because it's computed at compile time. It will never be changed at runtime. We do everything at compile time. So it's okay to be static and constant. Static is bad when it's variable. Here it's not, it's a constant. It's a static constant. I'm completely cool with that. So it's a static constant. This is the type value. And now we're going to start using the n. What you find is that value is n times, and then it's invoking another type. Actually, it's fetching the value that's embedded in another type. It's fetching the value that's embedded in the type fact of n minus 1. That is, if I had the type fact of n, I created the type fact n minus 1. So if I had the type fact 5, I got a type fact 4. Inside fact 4, there is a value which is static and constant, so it's known as compile time. And I take that value, multiply it by n, and I say this is the value that's in my type, fact 5. Make sense? Now, how do you stop this? Well, as always, you need to give a base case to your inductive definition. So you say, bottom case, struct fact 0. That is, you have specialized this family of type. This is defining a whole family. Here I'm specializing and I'm giving a slightly different definition for one member of the type family. Fact 0, I define to be the value, still a static constant, same type, right? But the value, I don't define it with an expression. I hard code it to be a constant 1. Now you see what's going to happen. If I ask for fact 5, the compiler will say, oh, fact 5, that's great, it needs to have a value, but to produce the value, I need to compute at compile time fact 4 and pick up its value. So he creates a type fact 4. To good that type, he uses this stanza and he creates a fact 4 that has a value which is 4 times the value embedded in fact 3, which he compiles again at compile time. So fact 3 is 3 times the value of a fact 2, which is 2 times the value of a fact 1, which is 1 times the value of a fact 0, and fact 0 he says, oh, I'm not going to use that, I have a special form for fact 0. It also has a value which is 1. So you end up saying, hey, that's cool, I know what this is, it's 1. So now he takes the product of all the values embedded in the fact, computes 1 times 1 times 2 times 3 times 4 times 5, ta-da, y is 120. You see everything happened at compile time. I didn't run the program yet. Does that make sense to you? There is one fundamental idea here. We compute with types. We create oodles and oodles of types. Inside the type, we're going to put things, the value we care about. So we're creating type families that contains the object of interest, which is a value. Now, this is important. I wanted to refresh your memory. We had already seen it in an earlier lecture, but I wanted to make sure we were all on the same page and you saw the mechanics of this were fresh in your mind before I'm actually going to show you much more interesting stuff being embedded in types. But the mechanics will remain the same. This is one of the fundamental ingredients. We'll see a second one very soon. You've already seen it. I'll just refresh your memory on it. But that's the mechanics. Now, if I have my variable y, that's cool. Now I can print it. So the program here has a value embedded inside, which is y. It's equal to 120. And all it does is that it prints 120, game over, right? So you don't have to actually believe me, right? It's good to be a disbeliever. Grab your favorite compiler, impose the C++14, use the program, which is this one, right? Nothing really shocking. Use that program and simply use these two options. -S is to ask to emit assembly code, and I say, don't show me Intel code, I'm kind of allergic. Show me LLVM, which is the compiler tool generator that Clang is based on. And it's much more readable as an assembly. It's a high-level assembly, quite readable. And dump the entire thing in factmp.ll so that I can take a look at that assembly and see whether it makes sense to me. Okay, so you do that, run it. Here is what you see, right? Nothing too exciting. That's the entire assembly, by the way. You see all the options for the compilation and whatnot. You saw that I did this on my Mac. I'm putting the program here so that you remember. This is your main function. Define i32 main. It's a main function that returns an int, i32, right? If you have never seen LLVM, I'm just telling you exactly what's going on. So here you see that there are a couple of stanza, which are assembly level instruction. The two allocate here are just like allocate in C. It's to get space on your stack because we're going to host some temporary variables or variables like y. Y is a variable, so we need to have space on the stack. So I allocate two integers with a 4-byte alignment, and then I store in the first guy 0, and then you see here that I'm storing in the second guy, %2, the value 120. Wait, I never mentioned 120. That's the compile code. So indeed, the compiler computed 120 at compile time, got rid of all the struct, right? They don't even show up in the program. He just extracted the value and stuck it right in here. Then once he has put 120 in the temporary number 2, he loads the temporary number 2 in temporary number 3, he copies it, and then finally says, oh cool, let's return that. That's the return value. So that's the return y. So you clearly see that this y and %2 are the same thing, right? %2 is the name of the temporary when you look at the machine code. That's the temporary hosting variable y. Person 3 is another temporary, and you see that he reads from Y in order to implement the return. So this line here is really the return. That line here is really this instruction. That's it. That's the reassembly. That's compiled in debug. If you compiled in optimize, you would see that the code would even be shorter. He would get rid of the allocate because he realized you're loading 120 and returning it, so the program would melt to return 120. That's the same thing in optimized mode as -3. This is what you would get. We're good? It's kind of cool to actually see this happen, right? So the generated assembly has the function factorial completely evaluated. At runtime, I just return a constant, right? So if I run this program, I just see the constant, but I could just look at the assembly and see the result of the computation. That's kind of neat. Now, of course, you wonder, like, okay, cool. We can complete factorial at compile time now. Paint me impressed. Why? Why do we all do all this, right? Well, as I said, this is purely academic with factorial, but metaprogramming is actually very, very useful, and you will see that. And one of the main things is code generation. You can do certain tasks at compile time, in particular, do the equivalent of generating code and then using that code at runtime, right? You generate what will run. It's quite flexible. So we're going to take that. You will see what's going on when we do that, okay? Good. So this application, I want to thank Joe for showing that to me. He showed me a cute language I didn't know, right? I don't know all the languages, I reassure you. But it was kind of neat. It had a cute application, and the language, even though it's not available yet, was basically about a language made by a guy who's doing games, right? His whole story is, I want to make games, and there are certain things in programming languages that you can do a lot better if your language supports game writing. And one of the things he was harping on is that, yeah, there are tons of stuff, but one thing that's really cool is this metaprogramming business, the ability to run code at compile time where the code is written in the language you have. So he actually created a language that had that capability. And Joe said, ask my opinion. What do you think about this? And I look at it like, that's a cool language, but I can do the same thing in C++, hence the extra lecture, okay? So because I think that this is a real application, it's in the gaming domain, so it's relevant, even though you'll see, I just took out a small interesting part, but at least it shows you something that people consider real and are writing articles about and making lots of YouTube video about. So yes, I also watch YouTube every now and then. If you want to have more detail, ask him, he knows where it is. I'm not going to bore you with that, but this is all about color management, right? When you do games, you have to do things like putting pixels on the screen. Right? The days of games that are text-based are over. Now you want to have fancy stuff, right, for your retina. So we're going to put colors on the screen. And the main point is that, I don't know how familiar you are with color theory, but you know that there are multiple ways to represent colors, right? You can use luminance and hues, you can use saturation, you can use RGB, there are many mechanisms, and even in the RGB space, there are multiple different formats for RGB, right? So that's what we're all trying to do. So you must have seen pictures like that, right? That's showing you a color space in the CIE representation where you have two axes, X and Y, that are between 0 and 1, and that give you the chroma, right? It's the amount of color you have for two bases. And what you find is that typically the white is somewhere in the middle. Actually, there is a dot here, which is the pure white. It's in the middle of that shape, okay? Now, it's kind of cool, and this is the space, right? This whole thing is what our human eye typically sees, okay? So this is a representation of the color we can see. What you find inside the triangle is an approximation of that. That's what the sRGB convention used by Adobe can actually represent. It's not as good, right? You can only see some of the things, but you get most color. You get the green stuff, you get the blue stuff, you get the red stuff, and anything in between, including white. So sRGB is just the triangle that's inside. Now, if you have a a scene you wish to render, and you know the color to the human eye, you need to compute what that color would become in the sRGB space, because guess what? You need to put that on a display, and that display supports, check on your display, you see there is a button to choose the color space, it supports something like sRGB. So you want to do that conversion, okay? So typical, you have a mathematical model of the color you want to show as a triplet RGB in the CIE space, right? Actually, it's a XYZ thing. And you want to convert it to an sRGB value that falls in that triangle, and it's an approximation of the true color. Okay? So how do you do that? You have a formula. The big C here represents one of the three fundamentals, red, green, or blue. Okay? X, Y, or Z. And the formula is like this thing. It's a case analysis. If the value that's the linear value, so the red, for example, is less than 0.03, remember, red is down here, green is there, and we're between 0 and 1, right? So if this is less than this value, you multiply it by 1292. If it's more than that value, then you do this funky formula that consists in raising C to a fractional power, multiplying it by a coefficient here, where A is this value, and then subtracting A, and that will give you the transformation. You want to know why the formula is done that way? Study color theory, that's not my point. The thing is, you need to realize that if you have to display 1000 pixels by 768 pixels, 1024 by 768, for each of these pixels, you have to compute this function 3 times. For the X, Y, and Z, for the R, G, and B. Then you know the value of the pixel, you can put it on the screen. Okay? Realize that this function involves raising a number to a fractional power. You're going to be cranking your CPU, my friend, just to put 1 frame. Remember, you're supposed to put 24 frames a second, and these days, even my son tells me, like, 24, like, nothing below 60, Dad. You need to put an awful lot of frames, and your screen is really 1024 by 768? No, right? Who has a 4K screen? Okay, I got it. I have a 4K. That's an awful 4K, right? That's an awful lot of pixels you gotta put out, okay? So you have to do this very efficiently. So yes, the mathematical definition is straightforward. And we can implement it, point in case, here it is. Ta-da! This function, real linear to sRGB, remember it computes it, the float value is in between 0 and 1, 0 and 1, and it's just implementing that, and we're going to call this 3 times. 1 for red, 1 for green, 1 for blue, right? Generic. Takes a value between 0 and 1, and it spits out a value between 0 and 1, which is the RG or B in the sRGB colors. Okay? So, and you notice that it's computing power F to the fraction. Right. We're good? Awesome. Awesome. Oh, yeah, I actually included the link. It's great. But it sucks, right? It's horrible. This thing has an if-then-else. Why is an if-then-else bad? Come on, that should be immediate by now. Why is an if-then-else bad? Yeah, it's horrible for a pipeline. Each time, he's going to have to know, am I going left or right? I don't know. Let's put in some bubbles. Try to execute speculatively. Boom, Spectre, right? I mean, you have attacks directly hitting you. It's like, this is a bad thing. So we put bubbles, we slow down the code, and we do this each and every single time. Then we call a function of the math library, a function call. How many instructions to do a function call? In assembly. Okay, a lot. What qualifies, to give you a sense, right? A lot is probably 100 to 150 at the minimum, just to do the code. I'm not even saying what power will do. And then it's a fractional exponent. It's not just a sequence of multiplication. It's more complicated than that. So this is a nightmare, right? We're talking thousands of instructions just to compute one entry with a good test in between to just make sure we go as slow as possible, right? So if you are a game writing software engineer, you look at this and you run in the opposite direction saying, you're raving mad. This is never going to work. It's too slow. And you'd be right. So there is a solution to that, And it's basically the idea is to use what's called a lookup table. You compute all the colors for all the intensities you care about. So since your display takes value between 0 and 255, you pre-compute in a table the value of the linear to sRGB conversion for every value between 0 and 255. Right? Remember, 255 is like 1, so you scale, right? Whereas 0 is 0, right? So 0 is 0, 255 is 1, compute everything in between, you have the colors. Okay? So this is how you want to do this. You do a lookup table. And you say, cool, I know how to do this. I write a little piece of C code, right? Here it is. Define my size of the table to be 256. And then I print C code, float sRGB table bracket, sRGB table size bracket. So I'm creating an array of float. And I put a curly brace. And then I write a loop that print %f%c, so it prints a float and then a character with a white space in between. And the float is what? Well, it's real linear to sRGB I divided by the size. So yes, I take my index, then I divide by 255. The last entry is 255 divided by 255 is 1, right? So indeed, I'm covering the full range 0, 1. And then I print that value. I call the function, and I print a comma or a white space so that this thing is readable. At the end, I put a curly brace. If I was good, I would also put the same column. And when I run this program, guess what it produces? A little piece of C code that you can then include inside your code. And now you no longer call a function. You just go look up in a table. How fast is that? How many assembly instructions to look up a value in a table? Come on, you should know that instantly. 1. It's an indirect load. Okay? 1. We went from thousands, like a minimum, to 1. Just 1. Lookup is the way to go. If you want speed, nothing beats 1. I'm not even talking in theory of 1. I'm talking really 1, right? If we are a software engineer in gaming, we really care about the constant. Okay? So this is not 1, this is 1. 1 can't go any faster. Okay? So that's the best you can do. Great. It works, but now you have two kinds of sources to maintain. The source that generates the source that you have to copy paste into your source, then compile your source to get the executable that does the work. Okay, that's cool because you have one left. Now imagine you have a bunch of different transformations and you have to do this for quite a few things. What's going to happen before long? Well, you will forget to recompile the code that generates the code, right? And you will put copy-paste of the generated code everywhere. And if there is a bug in the copy-paste generated code, you're going to have trouble. So even though in the lookup table it sounds fairly simple, this is a real issue. And maintaining the code generator, the copies of the generated code is tricky. You don't want to do that. You are in a programming language. The best thing to do is ask, please, programming language, help me do that. I don't want to do any of this business of generating code and using a set script and injecting that into my real source code. If you are a little bit of a Unix person, you can already see like sed and awk and make files and how to glue all of this automatically, but it's a nightmare, right? You don't want to do that. You write a piece of C++ that does everything. This is what real men do and women. Okay? Good. So humans are better at that. So we want to do everything in one shot. So we're going to do that, and we're going to look at the number of examples to get there, right? And I start with traits. Traits are all over the place in C++. I never talked about it, but I show a trait built from scratch. So at least it will give you a sense of what it is. Now, later on, when you see traits in reality, you'll know what these are, and they won't be too scary. Okay? Good. So let's get going. My plan is to write code that will run at compile time, and I want to use it to fill a table, to build that lookup table at compile time, so that at runtime I can do everything in constant time. One assembly, that's the reason. Cool. So the first thing I'm going to do is introduce you to a new bit of C++ called const expression. I haven't talked about it, But it's kind of neat. You can use it in tons of places. And what it does is that it's a mechanism to say, oh yeah, here is an expression. Compiler, you should know that this expression does not depend on any values at runtime. You are free to evaluate it at compile time. We're home, right? Const X, that's all we need. Why am I spending a whole lecture on this? Right? Because they're caveats. Const X doesn't work with everything. That's the doc. If you want to follow the URL, you should. But the thing is that a const X can be used in any constant context, but a const X cannot contain everything you want. There are restrictions. Certain things cannot appear inside a constant expression. And that creates headaches. Now, as C++ evolved, they have relaxed some of these limitations. Older versions of the C++ standard were even more restrictive than C++ 14 or 17. With 14, it's pretty cool. You can do some pretty scary stuff. At some point, you couldn't even put an if then else in a const text. You had to use question mark column. That was cool, but not if then else. Now you can use if then else. Much better. Okay? So that's an example of a restriction, but that one was lifted. So we can use if then else, but there's still other restrictions, right? So we need to worry about this. So here is my factorial again. And all I've done is that I've stuck const X in front. Now I've written it with an accumulator style. That is, I have my input integer, which is now a constant. I'm tagging this as a constant. And I have my sum, which is a constant with a default value of 1. When I'm in the base case, I don't return 1. I return the sum, it's an accumulator style. And what I pass, of course, is I pass the product. Okay, if I go down. So pretty straightforward. I write main factorial 5, 1. I compile that. What do I get? Well, it's kind of neat. You're going to get a program that contains the constant 120. Same story as my template. So here, I didn't achieve metaprogramming by computing with a family of types. I achieved metaprogramming by taking a vanilla C function that I wrote myself and annotating it with const X for making sure that the inputs are constant. So that the compiler understands, no, this thing cannot depend on anything at runtime. And then when I evaluate factorial 5, I get back a value, and that's what he's going to store. That's cool, right? It's even better than the template. You're really writing vanilla C++. And you feel really good at that point because you realize all of a sudden that this even works for recursive code. Factorial is recursive. I have a recursive implementation, and the compiler still does it. He can actually take that piece of code and run it at compile time, get the value, and embed the value in the assignment that you see here. Okay? That's the neat thing. You can even do slightly better. You can stick a const X in front, and he will even generate slightly better code because now he knows that that Y cannot change. The Y is known at compile time. So because the Y can be known at compile time, he can know that it's a value 120, and therefore he can generate just like before. Return 120. Wash your hand, walk away laughing. Const X is the best thing ever. Of course, it's great until you hit the limitations, right? So that's cool, and we're feeling good about this. Any questions so far? That's the second concept I covered, right? We've done computing with types, and now you see that you can actually achieve the same result with const X for functions that are reasonably simple.
So could you repeat what adding const X to the declaration of Y adds? Yeah.
If you have it like this, he will compute 120 and stick it in Y, but Y will still be a variable on the stack because it is read-write, and at runtime you could modify Y afterwards. He doesn't know that. So he needs to treat it as a variable that can change at runtime. Factorial doesn't, but Y is now a variable. The moment I stick const X here, you're basically telling it, no, this is not a variable. It's a constant whose value is known at compile time. So therefore, if you are using Y in tons of places, everywhere you see a Y, you don't put a reference to Y, you stick 120 everywhere. It makes it constant and known at compile time. That's the main thing, right? Known at compile time. Therefore, good? Yes.
If you value a constant expression, can you
known at compile time. remember that that's the thing, right? You need to see, for example, it cannot depend on anything that you read at runtime, on data structures, or anything like that. It has to be purely dependent on things that you already know at compile time. And if you try to feed to a const expression something that's known at runtime, C++ actually will not scream at you. It will generate a conventional function. And things will fall back to happening at runtime. So think that const text is not forceful directive. If he can't generate it compile time, he will generate it runtime. Okay? So, which is why sometimes it's good to go look at the assembly and make sure, am I really getting what I think I'm getting? Right? Particularly if you use const x, because these are traditional functions, so you can still generate the traditional function. Okay? So be careful with const text. It's easy to deceive yourself into thinking it happens at compile time. So I always go and take a look at my assembly code to make sure, am I really getting what I think I should be? And you know how to do this, right? -s/lm, you will do. Good? We're good on that? Cool. So, easy, right? What did I change? I took my real linear to sRGB and come on. I put const x and I'm done. Awesome. Awesome, right? Awesome. No, come on. It's 9:35. Can't be done. It can't be. That would be too good. Now there is a problem. There is a problem here. This won't fly. Why? Because you're calling POW. And POW is a function that's part of the C library, and it's meant to run at runtime. It's not implemented in C++. This compiler doesn't have the source of that. It's in the C library. He's not going to do it. You won't. He will tell you, no, sorry, can't do that. I hate your function. It's horrible. It's not a const text. It's going to actually generate something that runs at runtime, not at compile time. So you won't get what you want. If you were to call that function, you wouldn't embed the output of the function in the executable. You would actually call the function. You would be back to the good old fashioned. So it didn't improve anything. If I do that, it doesn't work, right? Because I'm calling POW. But conceptually, if you look at that, should that work? Yeah, I could stick in a const here as well. That would be good. Well, in this case, it won't make a difference, but yes, it would be better to even put a const. Note that if you don't put it and he figures out that the context is really constant, he will manage even without the const. So it's good to point out. The const is not mandatory. It helps the compiler figure out that there are no side effects in that, right? So I tend to put const. If it's a const text, things should be const, right? So there will be const everywhere in the code I tend to write. But here, that's not the showstopper, right? Even if we had put const there, we would still be stuck because of that. That's the real pain. So if it's the real pain, but look at the rest of the function, right? It's an if then else, it's a bunch of multiplications and divisions. Right? Should it work? It should, right? So, and it's all because of POW. So what's your reflex? What's your gut reflex? What's your gut instinct when this happens? So implement POW yourself, right? POW, how can it be, how hard can it be? X to the power P. It's easy, right? X to the power P. F to the power 1 over 2.4. Can be difficult to do, right? How do we do that? X to the 1 over 2.4. Okay. Now, guys, you have taken algebra, remember? I know it was high school, or maybe even middle school, I don't remember. How do you do that? F to the 1 over 2.4. Okay. That's not the answer I was looking for. Thank you. Oliver, I know you can do better. You Google it, then you don't find a clear answer, and you will find all the stuff about integer powers, because that's what's in homework usually. But here it's x to the 1 over 2.4. So you won't find a version that, all your version will be int. Then if you put that in your homework, the prof is laughing, because of course that's not what he asked, right? How do we do this with a fraction of power?
You probably still use the same properties of exponents that you use for integer power.
We're getting somewhere. Now, intelligent being speaking, let's go. Let's do this.
Oh, God. I mean, so if we just always, do it recursively the same way we normally do it, and then when our power is close enough to 1, we stop.
Like okay, we could try that, right? So I'm going to accelerate the process. It doesn't work,
yeah.
Right? But you can be smart, right? What does it mean x to the 1 over 2.4? What do you know about exponents?
Reciprocal of x to the 2.4. No, not that. Not reciprocal. Something else. It's a square root.
Okay, well, you're getting somewhere, right? X to the a over b. X to a fraction is the bth root of x to the a, where a is an integer, right? So it's the integral root, the bth root of an integral power, x to the a over b. Do we have x to the a over b? Give me a, give me b. 9 and 5. I think you're onto something not quite correct in your exponents, but I think you're thinking the right way. Try again. Anybody can try, right? And you can say what you're doing as well. 5 and 12. Brandon wins. Why? Because 1 over 2 to the 4, it's 10 over 24. Right? And it's not 10 over 24 we have, right? It's power 10 f 10 to the over 24, yes. So 10 to the 24 is what? It's 5 to the 12, because I simplify my exponent. So that's the 12th root of the 5th power. We know how to compute. Now you use Google. Or you just remember how to compute powers, repeated multiplication, right? And you know how to compute roots, right? Roots are easy. You use Newton's method, right? You make a guess, you use the derivative, and you get closer. Right? Just apply Newton's method. Even Google will tell you that. We good? So there we go. We have everything. We know what to do. We can actually re-implement this ourselves. We just need an integer version to compute powers. Because there is one in the C library, but it's going to give us the same problem, right? It's not going to be a constant. So we need to have raised to a power, compute a root, and maybe a few other ancillary things. So we get to work, because we want to get rid of our pow, and it's not going to be too bad, right? We want to have that const x, and we're going to build everything, right? So I'll show you how we build that in a second. But here it is, in its full glory, power b to the e, okay? Note that it's a float to an integer power, and my accumulator, as long as e is not negative, I multiply the accumulator by b, I return, and this is a const x. Notice, to your point, I didn't put const on either of these guys, but I should read it. I should put const, it would be cleaner. Okay, so this is power, integer power. Then for a root, nth root, give me the pth root of v, okay? P is how many times I want to compute the root. V is the value. So how do you do that? You start with an initial guess, and you're simply going to say, fine. So if you're asking for the 0th root, well, we know what that is. It's 0, it's boring. Otherwise, I have my Newton iteration here that basically computes these things. And if you look at it, it's the Newton theorem, right? It's y is equal to x minus the derivative over x, the derivative of x divided by f of x. Okay, so you just use that formula, you compute the delta x here, you update the xi, you go on as long as the difference is greater than some threshold, because you're approaching the value. And when you get out of the loop, it means you're close enough to the true value, you're not improving, you're not getting sufficiently closer anymore. Right?
that the improvement is not good. So at that point, you can stop and you return. Now notice that this calls a const exp, and everything else is just arithmetic and a while loop. Oh, it calls my abs as well. Well, why did I implement my abs? Because I couldn't use the abs that's built into the C library for the same reason. So I implemented my abs and made it const exp. And of course, my abs is straightforward. All right? I still write functions like that. One line, it's a beautiful function. My code is readable. Are you with me on this? Right? So this is purely Newton's method, right? Approaching, you start with a guess, you use the derivative, you shoot array, you get the next guess, and when you see that your guesses are producing images that are close enough to each other, you can start. Okay? That's cool. Now I can write real linear to sRGB is the 5th power, 12th root, and then the rest is exactly the same, and it's a constant. Who's with me? You have nothing? Who's lost? Nobody's lost? That's cool. Now you see that the heavy lifting is all written in C/C++. Okay? I just stick this const exp in front of everything. All right? But I have a solid implementation at this point that I can run. Maybe it's worth. Let me check if it makes sense to actually run this so that you are convinced that this works.